Hello, year 12. How's things? You all good? Have a nice weekend? Bank holiday weekend? All good? Right, brilliant. Back to work then. So, what we're doing about today, a very quick video today, is on Kirchoff's law. Now, apparently, Kirchoff is not the official pronunciation of his name, it's more Kirchoff. His name is Gustav Kirchoff. So, but I've always known it as Kirchoff, so you'll have to forgive me about the pronunciation. Now, Kirchoff, he had two laws. One involving PD and one involving current. Now, these laws are really useful in circuit analysis. In fact, they're essential to understanding circuit analysis. And when we get to the point where you're kind of really having to break down circuits, these are laws that you can hang your hat on. They are part of your detective work, if you will. Right, so I'll go first. I prefer to go over Kirchoff's second law, right? So second law. I know, why would you not start with the first, sir? Well, I get that, but hopefully you'll understand. Now, Kirchoff's second law, and by the way, you don't need to know that it's Kirchoff's law, you just have to understand the concept, but I think it helps us to remember it, in my opinion. It is about PD. So what does it mean? So let's have a look at a most basic of circuits. We've got a supply. What do we call the supply? The EMF, and we've got a load here which will give us a voltage. So if I supply the circuit with 3 volts, as you know, that's 3 joules per coulomb, right? Then what comes into the circuit up here will inevitably disappear down here, so it'll get used up here. So this voltage here will be 3 volts, 3 joules per coulomb, right? Can't change that, that's just the way it works. Now, if we've got 3 volts going at the top, 3 volts at the bottom, we'll call that pretty much an application of the law of the conservation of energy. You can't have more energy down here than you had up here, and you can't lose any more down here than you gained up here. What about when we split it then and we have a series circuit? So this time I'm going to have not 1 bulb but 2 bulbs in series. So Kirchoff's second law talks about series circuits, really, about the PD, how that works. This time I'm going to supply it with 6 volts of EMF. What am I going to lose over both bulbs? Well, that's the only load in the circuit, so I'm going to lose 6 volts here, right? But that doesn't imply what I'm going to lose over each one. So what will I lose over each one? Well, assuming they're the same resistance, I will lose 3 volts there and 3 volts there, right? Adding up to the 6 volts that came in. So this is essentially what Kirchoff's second law is. Kind of summarises as this: the sum of the PDs in the series circuit is equal to the EMF supplied. Right? So the sum of the PDs, so that means all the PDs, all the loads around the circuit, will equal the EMF supplied. What comes in goes out. It's pretty obvious in a way, but you know, it's something that in a series circuit we can rely upon, that rule is happening. So let's just quickly think about a situation where something might be changeable, and I'm going to send you some questions to sort that out. Drop my pen. Right, let's say I've got a series circuit here I've got a bulb, a resistor. So let's say this is 9 volts going in here, I've got 100 ohms here, this is 50 ohms here, and this is 75 ohms here. Now they are not, as you can see, the same resistance. In fact, let's go and get a calculator. How could I find out the total current going through the circuit then? So we know from Ohm's law that I equals V over R, and this would be the total supply voltage, and this would be the total resistance. So we've got 9 volts here over the total resistance, which is 150, 225 ohms. So 9 over 225 is equal to 0.04 amps. So it's going to be very useful to put this on here, 0.04 amps. Now one of the tips that I've picked up over the years is to always find the current going through the cell or the battery. Really useful. And basically speaking, what voltage drops would we have over here? Well, if we have 9 volts coming here, we know one thing from Kirchoff's law, that it will be the PD across here, the PD across here, and the PD across here will equal 9 volts. But what's the split? Well, if we know the current, we know the current is going through each one the same. The current in a series circuit doesn't change. That's one of our circuit laws. So it's always going to be the same current going around the circuit there. So that we know then, let's take this one here. This is V equals IR. I equals 0.04 times by R, which is 100. So it's going to be 4 volts, isn't it? Don't need a calculator for that one. Just to double check though, because it makes easy mistakes are made when you get cocky. 4 volts. Okay, so if that's 4 volts, well, we can make, let's calculate the second one. Hopefully you know that it's half the resistance. It should be half the PD, but let's calculate it. We got V equals IR equals 0.04 times by 50. 0.04 times by 50 should equal 2. So we've got 2 volts across here. Now using Kirchoff's law then, we can be confident in saying that if we have a 4 volt drop across here and a 2 volt drop across here, what will we have over here? So we've got 4 across there, 2 across there. Using Kirchoff's law, we know the sum of all these PD drops across here will equal what was given in EMF at the top. So 4 plus 2 is 6, so we can be confident in saying that that drop there would be 3 volts. Okay, so that's going to be a 3 volt drop across there. Does it work out that way? Well, 0.04 times by 75 is equal to 3. Alright, so that's how we use Kirchoff's second law to obtain a mystery voltage, or you know, if we're in a, let's say we're in a circuit where we've got a parallel network here. It's making this up, of course, and this is 12 volts here. Well, we know that we're going to have 12 volts across here, but we also know that we're going to have 12 volts across both of those. Now, depending on the way that the current is distributed between those two branches, you know, we've got I going in here and then it splits off that way. That's what we're coming to in a minute. We know that we can, if we can get a voltage across here, if we know we've got 12 across here, then if we can get this one, V1, well, we can calculate what V2 is, because it's going to be 12 minus V1, or vice versa, and so on and so forth. Okay, so that's a really useful law, Kirchoff's second law, and it involves PDs in series. All right. So the questions I send should be used in applications of these and other things such as resistors that you learned about. Okay, Kirchoff's second law. It feels really weird saying Kirchoff. I said Kirchoff for so long. Kirchoff's second law, right, so Kirchoff's second law involves current. And I want you to imagine a scenario where we've got a junction. And we've got two currents going in, we'll call this I1, I2. And we've got three currents going out. We've got I3, I4, I5. Okay. Right, so we've got two currents going in, three currents coming out. Kirchoff's current law, or Kirchoff's first, what are you doing, sir? Kirchoff's first law. Sorry, guys. Kirchoff's first law is saying that the two currents going in, I1 plus I2, will equal the three coming out. I3 plus I4 plus I5, right? It's basically the law of the conservation of energy. What comes in goes out, right? And that works for, you know, any number of currents. You could have 1,000 currents coming in and 2,000 currents coming out. All the currents coming in would equal all the currents coming out of that one junction called a node, a bit like a stationary wave node, right? So let's look at this in practice. Right, so we've got a parallel network here. Let's keep it really simple to start with. And we'll have 3 volts going in there. What would we have across this one here? You should be comfortable with knowing that that's 3 volts and that's 3 volts as well. And let's say that we've got this is 100 ohms and this is 50 ohms. Alright, so what's going to be the current going through this one then? Well, we've got 3 volts and 100 ohms, so V equals IR, so I equals V over R. V is 3 divided by 100 is going to be 0.03. So going here we've got 0.03. Down here we've got 3 over 50. So 3 over 50 would be 0.06. So what is the total going in there? So we've got 0.03 amps going down there, we've got 0.06 amps going down here. So what is actually going in? What is going in here? Right? And what is coming out? Well, at this junction here, we've got 0.03 out coming out there, 0.06 coming out there, so this must be 0.09 amps. And coming down here we have 0.03, going to be over 0.06, so this is going to be 0.09 amps as well. Could we work that out? Could we calculate it out just to prove it? The total current going through the cell would be 0.09. Well, we could by combining these resistors. So 1 over R equals 1 over 100 plus 1 over 50. 1 over 100 plus 1 over 50 is 0.03. We will inverse that, minus 1. There's the button, there it is. Answer to the minus 1. So the total resistance here is 33.3 ohms. Therefore, the current going through is I equals V over R. 3 over 33.3 equals 0.09, yep, amps. So that proves, doesn't it, that the currents going through here split off. What relationship have we got then? With a higher resistance, do we have a higher current, or with a low resistance, do we have a lower current? The lower resistance will always equal the higher current, and the higher resistance will always equal the lower current. Why? Well, it's obvious, isn't it? Something with lower resistance will allow current to flow, and so on and so forth. So there's our two rules. I've done a whistle-stop tour there, but I try and keep these videos quick because it takes a long time to upload and whatnot. But that's a whistle-stop tour with Kirchoff's laws. The first one, the current law. All the currents going into a junction would equal all the currents going out. And you could get a question where it kind of, you've got 4 branches. Doesn't matter how many branches really, then they come together here and go off like that. This junction here, all the currents going through here, 1, 2, 3, 4, will add up to this one going in, and it will add up to that one going out. Of course, based on the different resistances, they'll have different currents. Alright? That's the first one, the current law. The second one, which is probably just as equally as important, you got the Kirchoff's voltage law, the second law, where the sum of the PDs in the series circuit will always equal the EMF supplied. The PD is where energy is lost, so just as an aside here, what would be the PD across that point there? What do you reckon? Well, hopefully you understand that that's going to be 0 volts in an ideal situation. Not in a real situation, but in an ideal situation. Why? Well, we treat the wires as negligible. We treat the wires as having 0 resistance. In actual fact, they would have some resistance, and therefore some PD would be lost across there. But when we test between 2 points, as long as there is 0 resistance between them, there will be 0 PD. So in actual fact, the sum of the PDs would have to include all the wires if they weren't classed as being negligible. And the cell. But that's for another lesson, that's internal resistance. Right, so that's that then. Hope you're looking after yourself. Please try the questions that I'm sending to you. Please try them honestly, and if you have any problems just encountered, just email me. Alright? Okay, speak to you soon. Bye bye.